Live now. All right, so a lot to go through, all of it's review, but I'm going to move pretty fast since we've already done this once before. I need to get us back up to, through normal distribution and z-scores and up to hypothesis testing for the homework for today. So let's get as much as we can within about 30 minutes or so. And then I'll start asking some questions on hypothesis testing. So going back from quarter one, looking at standard deviation. Standard deviation is a way to get an estimate for how spread out a series of numbers are. And the way that we came up with standard deviation is trying to solve problems that we had with other methods of trying to figure out how spread out a set of numbers are. The easiest measure of spread would be range. So if I've got a distribution, so let's say something like this, 3, 4, 5, 6, 7. I've got 2 3s, 3 4s, 4 5s, 3 6s, 2 7s. Okay, we can usually talk about a distribution in terms of its shape, center, and spread. Shape, center, and spread. So for this example, my shape would be a bell shape. I've got kind of a bell curve going on here with our distribution. My center, I could use mean, median, or mode for. Typically in statistics, we'll be using a median instead because it's less susceptible to outliers. Although if you've got a bimodal distribution, so a distribution that looks like this, where this is 3, 4, 5, 6, 7, it might be more useful to talk about your modes as having a mode at 3 and a mode at 7, rather than this middle point where you don't have any values for. And then spread, we could use range. We could use IQR, which is what we create our box plot in order to find, or standard deviation, which is what we'll be talking about today. Okay, so all of the SAT stuff first. Let me go down the line. Abby, what is a mean? Okay, I'll do that. So the sum of the values, and then divide by what? Number of values. Okay, so that's just an average. Is our mean. Okay. Eric, what is our median? Eric, can you hear me? Oh, I've got him on chat. Okay, so Eric's having some mic issues. I'm gonna pass for now over to Andrew then. Andrew, what is the median? Okay, median is the middlemost value. If I wanted to find the median for this distribution that I have in the bell curve, what would I do? Okay, I'm gonna draw dots here, I think. Okay, you're right. So I'm eliminating one number on the top and one number on the bottom, so my largest and smallest number from the distribution. Okay, and you're just going to keep doing that until you end up at the number that's in the middle. Okay, what happens if I end up here where I've got two numbers left instead of just one? Right. So I would average the two for the median. Okay, and then for the mode, I'm going to go back to Eric, who's on chat. Eric, what is the mode? Flash this so everyone can see your chat. Okay, I'm not actually sure if he's typing or not. Okay, I'm actually going to let Eric keep typing. Hopefully he's typing. And I'm going to pass while he's typing to Kyle. Kyle, what is range? Okay, range is the largest minus smallest value. Okay, mode is 5, you're right. Can you give me a general definition for mode? Or tell me how to find it. Okay, Nikita, while he's doing that, what is IQR? So it is a range, but it's a specific range. Okay. Yeah. Okay, so a box plot looks like this. It does have to do with the box plot. The IQR is actually this distance to this distance. So that's what quarter to what quarter? So the distance from what quarter to what quarter? See if I can help you out. So this vertical line here for our box plot is the median. So on my picture right now for the box plot, this distance that I've marked here from here to here is our IQR. This distance measures from what quarter to what quarter? Perfect. From the 25% mark to the 75% mark. So in English, we would say that's from Q1 to Q3. Okay, and Eric's answered up here. The mode is the number that happens the most. Occurs the most. Okay, IQR is the distance from Q1 to Q3. So if you wanted a formula for IQR, I could say the IQR is equal to Q3 minus Q1. Okay, any questions on our SAT stuff? Mean, median, mode, range, IQR? No. Okay, so that brings us to standard deviation. Are there any questions on mean, median, mode, range, or IQR? That's the SAT stuff that you guys need to know. IQR, okay. So our IQR is the difference between the median of the top half and the median of the bottom half of values. So the way that you would find that, I need to get a better data set than what I have down there. Okay, let's make a new one. So that data set's actually showing why IQR can fail. So let's say I have a data set that looks like this. Sure. Okay, so I have 13 numbers in my data set. My middlemost number is right here at 5, right? So this number here is our median at 5. So what I'm going to do is I'm going to split my data in half at that number. So that all of these numbers will become a separate data set, and I'll take the median again. And all of these numbers will become a separate data set, and we'll take the median again. That'll give us the median of the bottom half and the median of the top half of numbers. Okay, so that's going to give us our Q1. So take one from the bottom, one from the top, one from the bottom, one from the top. And then I've got 2 left here, so I'll get an average of 3.5. Q1 is 3.5. So that's the middle of the bottom 50%, gives us the 25% mark, is at 3.5. Again, same way that you got the median, only I'm looking at only the bottom half of numbers. Okay, I'm going to do the same thing with the top half of numbers. So Abby, if I want to get the median of the top half of the data set, what do I have to do? Okay, so here's the top half of the data set. If I wanted to get the median of this top half of the data set, what would I have to do? Do this in another color. Okay. Perfect. So that gives me 6.5. Okay, so all we did was I split our data in half at the median. For the bottom half, I got another median, and for the top half, I got another median. Okay, that gave us Q1 because it splits off 25% of our data set, and Q3. Okay, if I was going to draw this data another way, so if I'm going to write this out as numbers, it would look like this. 3, 3, 3, 4, 4, 5, 5, 5, 6, 6, 7, 7, 7. Okay, what we've just done is we've created our box plot by getting a Q1 and a Q3. So here's our Q1 in blue, our Q3 here in yellow, and our median, also called Q2 in green. Okay, Q stands for quarter. That means 25% of the data. So if you had 1 quarter, that's 25. If you went through 25% of our data, you would end up here at 3.5. If you wanted to go through half of our data, you would end up here at 5. If you wanted to go through 325%, so that's 75% of our data, Q3 would bring you here at 6.5. Okay, if I was going to draw a box plot, my box plot would look like this. So that's my lowest number here at 3, and my highest number here at 7 are my minimum and maximum. And then Q1 is the median of the lower half, Q3 is the median of the top half. Okay, my IQR is Q3 minus Q1, so that's what range would 50%, the middlemost 50% of our data fall in. So the range of values between the 75% mark at Q3 and the 25% mark at Q1 would be 6.5 minus 3.5 is 3. The middlemost 50% of values fall within a range of 3. Does that make sense? Okay. IQR is a little bit better than just a range, because if we had a crazy outlier, so like 3, 3, 3, 4, 4, 4, 5, 5, 5, 6, 6, 6, 7, 7, 7, 1 million. Well, my range would be 3 to 1 million, and that would make it seem like all of these values are really spread out. But my IQR would end up at 3 still, somewhere around 3. And that tells me that all my values are actually pretty close together. So IQR is better than range. However, IQR can fail. For instance, for this data set, my IQR would falsely imply that our numbers are fairly close together, when really you can see we've kind of got this trimodal distribution where we've got a bunch of values with spaces in between that never get hit. My IQR for this might show halfway between 1 and 9, halfway between 10 and 15, and then give me my range there. So most of the values fall within that range, which isn't really true at all. So if I want a better idea of how spread out these numbers are, the first thing we did was we tried to just add up the differences and then cancel the positives. The problem is if I just add up the differences, we'll always end up with something close to 0 because our numbers that are positive above the mean and our numbers that are below the mean are going to cancel out. So if I have numbers that are 4 units above the mean and numbers that are 4 units below the mean, we add them all together, divide by our total number of numbers, we get an average distance from the mean, which is 0. If I take absolute values, it gives me my average distance from the mean where I don't care about negative or positive signs, whether we're above the mean or below the mean. Looks good, but can give us a wrong impression. So something like this. 7162 values away from the mean and 4444 values away from the mean would actually give me the same deviation. So that's not what we're looking for. So eventually what we did was we came up with a value that's called variance. Okay, so variance looks like this, where instead of just taking those values away from the mean, we end up squaring the distance away from the mean for every value. And then we get our average of that squared distance away from the mean to get a really big number. But the bigger that number is, the more change that you have in your data set. So now you can see if I square all of these differences from the mean, having 7 units away from the mean is worth a lot more, 49, than this 1 unit away from the mean is worth, which is still 1. And so the more change that I have away from the mean, the larger my number becomes. So standard deviation is a measure of change. Okay, because these numbers are so big though, 64 divided by 4 and 90 divided by 4, in order to get them back onto a number that we can graph, since we squared all of these numbers, we just take the square root again, and that brings us down to a size that should be graphable with all of our data set. So that's our standard deviation formula. Standard deviation is the sum of the squared difference from the mean. So for every value, take your score, subtract the mean, and square it. And then after you've summed all of that up, divide by the number of numbers. That gives you variance. If you take the square root of variance, you'll end up with standard deviation, which is a number that the bigger it is, the more change you have in your data set. The smaller it is, the less change you have in your data set. Okay, any questions on standard deviation, what it is? Okay. So one of the key things we can use standard deviation for is to get what's called a z-score. So before I jump into that, we've talked about bell curves before. The cool thing about bell curves is that once you've standardized your distribution for a normal distribution, what the percentage of values that will fall one standard deviation above the mean is always the same. So even though what one standard deviation is will be different for every distribution, once you know what one standard deviation is, the same percentage of values will fall within that one standard deviation above or below the mean. So we call that a z-score. Z-score counts how many standard deviations you are above the mean. We can get it by taking any score you want and subtracting the average to get your difference above the mean or below the mean, and then divide by how much distance is one standard deviation. So if we had an average of 3.5 and a score of 4.5 with a standard deviation of 2. Then I could do this as, if our score is 4.5 and our average is 3.5, then I have 1 unit above the mean. So our distance here is 1 unit. If I divide that by how much distance one standard deviation is 2 units, then I'll get 1/2. Again, that's our score, 4.5, minus our mean, 3.5, divided by our standard deviation. One standard deviation is 2 units. Ends up with 1/2. And what it means is we are 1/2 of a standard deviation above the mean. 1 unit above the mean is 1/2 of a standard deviation above the mean. Okay, why it's important is because the same percentage of values will be enclosed by 1 standard deviation, which means if we know that we are 1/2 a standard deviation above the mean, we can figure out what percentage of values would fall within that range, which is what we do to find probability. Okay, I know I'm moving fast, but that's because we've done all of this before. Any questions so far? Okay, so one use for this is to compare different values. So as an example, I've got my sport and my brother's sport. So I used to do downhill slalom, my brother used to long jump. If we wanted to compare and see which of our scores were better, then we could do something like this. So I'm pulling these scores from the Olympics. So the results are really impressive for the long jump, and you can't really tell for the downhill slalom because it kind of depends on the course. But I've got our average, our standard deviation, and then what the gold medalist score was. We can see how many standard deviations above average the gold medalist was to see how impressive was the gold medalist score compared to other people in their sport, to do a comparison between two completely different sports. So for instance, for the downhill slalom, our z-score for the gold medalist would be the score of the gold medalist minus the average in that sport divided by the standard deviation in that sport. So in this case, it would be, for the downhill slalom, 87.93 minus 94.27 divided by 5.28. Okay, which if we do, gives us our z-scores for the downhill slalom. Our downhill slalom was 1.2 standard deviations below average. But our long jump score was 2.7 standard deviations above average, roughly. If I was going to graph that, it would look like this. So here's the slalom skiing, which was 1.2 standard deviations below the mean. And our long jumping was 2.7 standard deviations above the mean. Which do you guys think was more impressive? The long jump or the slalom skiing? Who are we on? Okay, I've actually just run through everybody, so I'm going to go back to Andrew since I just had Abby with a question. So Andrew, which is most impressive? Long jump or downhill slalom? Long jump. Why is the long jump more impressive? Okay, you're right, but if you wanted to explain this to someone who didn't really understand the math, then what does that mean? We're on the right track. So what it means is, compared to other long jumpers, the person who got the gold medal for the long jumpers, their score was more unusually good for long jumping than the gold medalist was for the downhill slalom. More unusual compared to other long jumpers. Then the downhill slalom's gold medalist was compared to downhill slalomists, other skiers. So they were both really good. These are the best in the world in their sports. But because the long jumper was so much better compared to other long jumping scores, his z-score is more extreme. Okay, any questions on what we're doing? Okay, here's another example. I want to know which one's more impressive, ACT score or SAT score for this person's results. Eric doesn't have a mic, so Kyle, what would I have to do? Okay, and for the ACT? Okay, so once we do that, how will we know which one we need to send to college? Once we do that, how will we know which one we should send to this person's university? Which one should we... Sorry, go for it. Okay, the one that has the highest standard deviation. Okay, C ACT. Okay, so I've got the results here. Which one would you want to send? ACT or SAT? ACT, because they've got the highest Z-score. Compared to other people who took the ACT during that session, their score of 28 was better than more of the students on that ACT than the SAT score of 1340. So the ACT score is more impressive, and they should send that one to the university. Okay, I think we've got this. So I'm going to skip ahead. If you guys did not have a calculator, then you could use a z-score table to figure out what percentage of values are enclosed between a specific z-score and 0. So your z-score table will end up looking like this. It's this giant table of z-scores. So if I had a positive z-score of 0.06, if I had a positive z-score of 1.96, then I would go down our z-score table until I found 1.9, and look down my hundredths table until I get to 0.06. So putting both of those together gives me a z-score of 1.96. Okay, a z-score of 1.96 will enclose between a z-score of negative infinity and a z-score of 1.96. 97.5% of all values. So that means if you got a z-score of 1.96 on your SAT, you scored higher than 97.5% of all people who took the SAT that session. For most of what I'll be asking you guys to do for your final exam, you will have a graphing calculator for this. So if you wanted to do this with a graphing calculator, you can use what's called the normal Cdf function. So this is a normal cumulative distribution function, or normal CDF, which takes an argument of z1 and z2, and it prints out the probability, so it's a decimal, of getting a random score between z1 and z2 on a bell curve. So for this one, I would type second distribution, normal CDF, negative infinity. Now, I can't type negative infinity on a graphing calculator. Does anyone remember what I have to type? Perfect. Negative 1 e to the 99. That e is scientific notation. So that stands for times 10 raised to the power of 99. Is just a really large number that I can put in my calculator, 1 times 10 to the 99th power, without giving me an overflow error, to a z-score of 1.96. Gives us a 97.5% chance that we would randomly have a value that falls within negative 1 times 10 to the 99th power standard deviations, or 1.96 standard deviations above the mean. Okay, which brings us to hypothesis testing. So for hypothesis testing, what we're trying to do is prove that there is a significant difference between our score and an average, which we'll do a lot in your science classes. For math, we usually start with what's called a null hypothesis. This is if nothing happens, what would be true? Null literally means nothing. Okay, so if nothing happens, what would be true? So, for instance, if I wanted to say, think I used fertilizer as my example here. So I've got a set of plants that is with fertilizer and a set of plants that is without fertilizer. And I want to see, does adding the fertilizer to these plants cause them to grow taller on average or smaller on average than my control group? My null hypothesis would be that our group with fertilizer grows about the same as the group without fertilizer. So if both sets grow equally, then nothing happened. Alternatively, if something does happen, then the plants will not have the exact same size as the ones without fertilizer. So in this case, there's two options. The plants could grow to be larger or smaller than the control group. So I really have two tails. They could grow larger or smaller in order to be significantly different. Normally, though, we'll be looking for a one-tailed test for this class. So that means I want to prove that the fertilizer causes the plants to grow larger, which would be this option. Oops, sorry. This one actually. If I want the plants to grow larger, then if nothing happens, the plants will be smaller than or equal to the control group. And if something does happen, our plants will be larger. Okay, so that would be a one-tailed test where our plants are significantly different if they happen to grow larger than our control group. So here's the average for the control group, so the plants without fertilizer. And then my average for plants that do have fertilizer. If it ends up being significantly different, so falling within the uppermost 5% of all values, or we could say the probability of having a plant without fertilizer grow as large as the plants did with fertilizer is less than 5%. Then we can say our fertilizer actually works and it does help the plants. So this solves a problem we've had in your science classes up to this point, where all plants are going to naturally have some variation. So if you just say this group has fertilizer and their control group does not have fertilizer, and then the experimental group with fertilizer grows larger, you haven't actually proven anything yet until you test for significant difference, because all plants naturally have different heights. So you might have just randomly lucked into getting plants that wouldn't have naturally grown taller regardless of whether or not they had fertilizer. Any questions on what we're doing or why for hypothesis testing? Okay. I think most of you guys remember this. This is the third time we've kind of gone over this now, since you guys had to relearn it for the midterm. So I'm going to jump ahead and we'll look at a couple example problems. And we'll see how you guys do. Now, I do think we've seen these once before. I can't remember for this class, but it's been a while. Okay, so I've just done Andrew. I'm going to go over to Eric, since you can type. If my average Japanese girl is born at 3 kilograms, the standard deviation of 0.4 kilograms, and Aiko, a Japanese girl, is born with a mass of 3.7 kilograms. I want to know, is Aiko unusually large for a Japanese baby? To have an unusually large mass. What would my null hypothesis be, and what would my alternative hypothesis be? Get my chat back up. Yes. Okay, and then while Eric is answering that, I just had Kyle answer another, so I'm over to Nikita. Nikita, what is my mu, what is my chi, and what is my sigma?
Mu is standard deviation, right?
Mu stands for mean, chi is my score, sigma is my standard deviation. So from top to bottom, this is mu, chi, and sigma. They're all Greek letters.
Okay, so mu is 3.
Okay, mu is 3 kilograms, you're right.
Then x is 3 plus 67 kg.
6, 7 kg, perfect. Standard deviation.
0.4 kg.
Okay, I'm going to point out your standard deviation here is usually not known for an entire population. So if you do keep going to a statistics class, you will usually see this represented as what's called a standard error instead, which is a number that's like a standard deviation but larger because we don't know the actual population deviation. I'm going to flash the formula for that really quick. So if we know the entire population standard deviation, so we knew every Japanese girl's weight ever born ever in history, so that we could calculate the exact standard deviation for all Japanese girls ever, then that would be sigma. And I'm cheating a little bit because I'm representing this as sigma as if we actually knew that number, when in reality we probably don't know what the perfect standard deviation is of all Japanese girls born in history. However, if we wanted to make an estimate for it, we could use what's called standard error, which is really similar, but we divide by what the square root of n would be from our sample standard deviation in order to give us what's called a standard error. What this does is this creates a larger number for our standard deviation, which gives us more spread. So instead of needing to be we'll say 15 units away for one standard deviation, I would now need to be 20 units away to capture one standard deviation, which makes it harder to get a significant difference. We're intentionally giving our problem more error, making it be more wrong, so that it's harder to get a significant difference, because we don't know what the actual standard deviation is. So, okay, let me jump over to Eric, who's just given us our null and alternative hypothesis. This is null hypothesis if nothing happens. Eric says this is our score will be less than or equal to the mean, which is perfect. Our score is chi is less than or equal to mu. Oops. Alternatively, chi would be greater than mu. We're trying to prove ICO is unusually massive. So our alternative hypothesis is what you're trying to prove. Your null hypothesis is what happens if we cannot prove that. Okay, does anyone remember what our alpha represents? Okay, alpha is the Greek letter, that's first letter in the alphabet. It makes an A sound. Alpha stands for accept, if that helps. Okay, alpha is the probability that we are willing to accept of getting a random value that would be significantly different. So if I want to be 95% confident in my result, I'd be willing to accept a 5% chance that I am wrong. So in this case, we could set our alpha wherever we want, but it's going to change our results for our z-scores. So I'm going to set my alpha at 0.5, which is kind of standard. 0.05 rather, which is standard. So that does mean I'm willing to accept a 5% chance that we are wrong. What that means is, as long as ICO falls within the range of values of the upper 5% of all Japanese girls on average, then I'm willing to say ICO is unusually large. Okay, how would I get my z-score? Back to the top of the order at Abby. Perfect. So that's, I guess I'll write our general form here as well. Chi minus mu divided by our standard deviation. Again, if you go to a statistics class later, since you'll almost never have the actual standard deviation, they're going to ask you to use what's called standard error instead, which I'll let you worry about once you get to your stat classes. But that's just another estimate for standard deviation when we don't know the actual standard deviation. Okay, so this is okay. 0.675. What are my units? Not kilograms. Z-score always measures how many standard deviations you are above or below the mean. So my units are actually standard deviations right now. So I could write standard deviations, or you could write sigma. If we are 1.65 standard deviations above the mean, or more, then we could say ICO is unusually large. Okay. How could I get our p-value? The probability that we would get a baby that is ICO's weight or more. Who am I on now? I'm on Andrew. So let me explain what we're looking for one more time. I want the probability that a random child would be 1.65 standard deviations or more. So it would fall within this range. Okay, as a hint, you need to use the normal Cdf function in order to get your answer. So what would I have to type? Oops. There's a 7 in there, I forgot. 1.675. And you're right, so that would be 1.675 to 1 e to the 99, which is positive infinity, but the largest number we can store in our calculator. So that's second distribution normal CDF. From 1.675 to 1 e to the 99 power. Oops, I missed. Gives us a 4.7% chance. So P is 0.046 or 0.047. I'm going to write. Okay, so is P less than or greater than alpha, Eric? Okay, our P is less than alpha. How confident can we be that ICO is unusually massive? Kyle? Okay, 0.95. 3, or 95.3% confident. And Nikita, what can we conclude? Too much. Here we go.
Sorry, I can't see the screen.
I want to know what our conclusion would be. If we said,
Yeah, what?
okay, I'm going to throw this on your WeChat just in case you can't see. Okay, that's what we've got so far. And here, there's your question. Okay, so what's our conclusion? I don't think I can get all this on one page. Sorry, guys.
Is that basically we could conclude that Python is abnormally heavy.
How confident are you that she is abnormally heavy?
95.3%.
Okay, we can be 95.3% confident that ICO is unusually massive. Okay, any questions on our hypothesis testing? All right, that was a lot for one day. Again, all of this was review though. You guys did great. I'm going to have you guys keep going with your practice tests that we've been doing. So for homework, same document as last time on your probability retest, which I'm sending again through WeChat just in case it's expired. So last time you did pages 1, 2, and 3. That was through binomials and geometrics. This time I need you to finish through your single variable statistics if you didn't do it last time. Your normal distributions and z-score section, which is the rest of this document, so the second half. So everything that you did not submit last time, I need you to submit this time. Okay, I'm going to be looking for that by the end of this week on Friday. So that's due Friday at midnight. The rest of the probability retest document. Yep. Because the rest of that document is 3 questions on normal distributions and z-scores, really. There is a z-score table provided if you want to use that. So if you don't have a graphing calculator, use the z-score table. If you want a graphing calculator, message me on WeChat. And I can link a graphing calculator you can use online. Okay, if you guys don't have questions, you're free to go. Thank you so much for coming. If you do have questions, stick around and I'll answer as much as I can. Thank you. Goodbye. Okay, Abby, what's the question?